So Darshana, you can start sharing your screen now.
Yes. It shows it has been disabled.
Just a minute. Can you try now?
Yeah, I'm able to do it now. Thank you.
Okay.
Is it visible?
Yes.
And am I audible?
Yes, you are. Please go ahead.
Okay, so good afternoon, one and all. Today, I'm here to present my thesis project characterizing the behavior of SN2013he, a Type-II SN supernova, using photometric and spectroscopic techniques. I'll be talking about what Type-II core collapse supernovae are and where SN2013he fits in it after a thorough investigation of its available photometric and spectroscopic data. Now, supernovae are broadly classified into two broad types, type 1 and 2, based on whether or not they have hydrogen lines in their spectra. Type 1 is further classified into type 1 is further classified into type 1A, 1B, and 1C, out of which 1A is the result of thermonuclear explosions. Type 1B and 1C, on the other hand, are core collapse supernovae and are classified over whether or not they have helium lines. Type 2 are also core collapse supernovae, but have, on the contrary, H lines, the hydrogen lines. Based on the shape of their light curves, they are further classified into type 2P and type 2L. In the light curve comparison plot, we can see that type 2P has a plateau phase of almost constant luminosity, whereas type 2L, the luminosity linearly declines with time. So what exactly are core collapse supernovae, especially the type 2 ones? They occur when massive stars of approximately 8 to 30 solar masses die in a catastrophic explosion, usually leaving behind a compact object such as a neutron star. They constitute 57% of all supernovae, out of which type 2 plateau supernovae occur 70% of the times. They depict strong H features in their spectra because of their hydrogen-rich envelope, and they release up to 10 raised to 53 ergs of energy in the form of neutrinos, 1% of which is converted to kinetic energy in the ejected material, and less than 0.01% of which is converted to light. So how do these core collapse supernovae occur, and what is their explosion mechanism? It happens when the star fuses all the hydrogen in the core to helium. As the rate of the fusion drops, the amount of energy released decreases and the core contracts. The pressure in the core is now high enough for helium to fuse to carbon. And once all the helium in the core is used up, this cycle continues as successively carbon is fused to neon, neon is fused to oxygen, and so on until we obtain an iron core of around 1.4 solar masses and a radius of roughly 1,000 kilometers. The timelines of these reactions have been marked on the cartoon diagram. The star basically forms an onion shell-like structure in the final stages of its life. In this high pressure and high temperature environment, the photo disintegration of iron and the electron capture reactions cause instabilities, and the star can no longer support its own weight against the imminent gravitational collapse. The infalling matter bounces off the dense core, creating a shock wave which further ejects it outwards. The large quantities of neutrinos produced in the electron capture reactions also aid in ejecting this material outwards. And as this shock travels through the star, it triggers various nucleosynthesis events. And once it reaches the surface of the star, it causes a spectacular explosion that we know as a supernova. So coming specifically to plateau type core collapse supernovae. So what basically causes the plateau phase of the constant luminosity, usually of 80 to 120 days in type 2P supernovae? The plateau phase starts when the fireball explosion begins to cool down. That is, the temperature starts going below 10,000 Kelvin, and the recombination of hydrogen effectively begins from the outside in. As the amount of ionized hydrogen reduces, the ejecta becomes more and more optically thin, and the photosphere recedes. But the constantly expanding ejecta keeps the radius more or less constant, and due to the recombining hydrogen, the temperature is also kept roughly constant at 5,500 Kelvin. Therefore, the luminosity during the plateau phase is constant. The plateau phase ends once all the hydrogen in the expanding envelope has recombined. The duration of the plateau phase has a strong correlation, has been shown to have a strong correlation with the V band absolute magnitude, MV, the kinetic energy and ejecta mass, or the radius of the progenitor prior to the explosion, etc. Now, coming to a rare type of Type-II Plateau Supernovae, the short Plateau Supernovae, which is the focus of this thesis. So they basically have a plateau duration of around 50 to 80 days. Various studies have suggested that they are caused by core collapse of massive red supergiant stars, which have been partially stripped of their outer H-rich envelope, probably due to enhanced mass loss through stellar winds. But what sets them apart from the Type-II L supernovae, which are also thought to be the fate of stripped envelope RSGs. So Hiramatsu et al. 2021 has shown that short plateau supernovae tend to prefer high 56Ni progenitors, and it has been proposed that the short plateau is powered by the radioactive decay energy of 56Ni. This, combined by a stripped H envelope, gives it light curve a unique shape, which lies somewhere between Type-II-P and Type-II-L. It is considered to be roughly 4% of all Type-II supernovae, but their detection is very rare because the mass it loses during its lifetime due to the stellar winds creates a shroud of CSM around the progenitor years prior to the explosion, and thus increasing the chances of dust formation and hence the extinction. So coming specifically to SN2013he. So SN2013he was located in NGC 4774, the kidney bean galaxy, at the given array and deck and location in the host. It is almost 400 million light years away and was discovered by Leonini et al. On the 9th of December 2013 during the course of an automatic survey of the Italian supernova search project. The galactic extinction due to the Milky Way in the direction of the supernova, as provided by the IR-based dust map, is roughly 0.042 max. And to calculate the host extinction, host contribution to this extinction, we use the popular method of estimating the color axis using equivalent widths of Na1D lines, Na1D doublet lines. They are a good indicator of extinction from within the host. And this method basically provides a host extinction of 0.37 magnitudes. And the total extinction, adding this and this 0.04 to 0.37, we get a total of 0.41 magnitudes. Now, to calculate like the NASA extragalactic database provides us a distance to the host as roughly 126 megaparsecs, but to estimate the distance to the SN more precisely, the indirect method of EPM is often used. So it is basically a geometrical technique where we compare the linear radii r with the angular radii theta to obtain basically the distance to the supernova. And of course, there are no direct methods to calculate either r or theta, but because the supernova as we see it is a point source and not an extended source as I have depicted in this cartoon. So these theta and r can be obtained through various indirect methods, such as theta can be obtained by fitting a black body function to the supernova fluxes at various epochs, and a dilution factor zeta has to be introduced to basically account for the fact that theta corresponds to the thermalization layer, whereas as I'll talk about it in the next slide, VPH, that is the photospheric velocity, which will be required to calculate R, that corresponds to the photospheric layer. So to basically overcome this discrepancy, which could lead to an overestimation of the distance by a factor of 1 by zeta, we add in this factor of zeta. And when this equation is basically rearranged in photometric terms, we obtain this equation that is in terms of apparent magnitude and extinction, where B lambda is given by this equation. And when we minimize this equation, we can obtain zeta, theta, and t. So now, although zeta is known to depend on various physical factors such as the density of the ejecta and the chemical composition, it can be correlated with the color temperature using this function. So when we feed in our temperature from the previous equation, we can obtain zeta, theta, we can obtain zeta, and when we divide it by zeta, theta, we can obtain theta as well. So finally, we have zeta, theta, and t. And now to obtain the linear red-eye R, as I said before, from we can use the expansion velocity. So the linear red-eye R can be derived from this expansion velocity of the supernova as R is equal to VPH T minus T naught, where T minus T naught represents the time since explosion. So VPH was calculated by observing the Doppler shift of the absorption minima of HE15876 angstrom line and FE5169 angstrom line. The data was then linearly fit, and the slope of which gives the distance, and the y-intercept gives us the explosion epoch. So the distance that we obtain agrees very well with the distance to the galaxy that we have from the NED database. And to confirm the explosion epoch, we apply another method to support the values that we have obtained from EPM. So we went back through some of the amateur astronomer data, that is the latest available images before the SN was actually discovered on the 9th of December 2013. So although the images are not exactly of photometric quality, it is apparent from the 1st and 7th December images that some object, albeit a little cloudy and foggy, exists at the RAN deck of the supernova 2013he. But no such activity is visible on 24th November 2013. So this implies that the SN must have exploded sometime between the nights of 24th November and 1st December 2013. And this also affirms that the results we obtain from EPM, the EPM method, are reasonable and fall within this range of dates. Now, coming to the light curve analysis of 2013he. So the figure shows the BVRI and GRIZ band light curves of 2013he as obtained by the performing photometry on the optical data provided by various telescopes, including those at Aries. So it is clear from especially the VRI and VRI light curves that the supernova was discovered during its plateau phase. It is difficult to comment on the light curve shape in the GRIZ bands because there's a large gap in the available data. Therefore, for this thesis, I have mostly focused on BVRI band data. So when the V band apparent light curve was fit by the given expression, this expression, it produced TPT, or the plateau length of 66 days, which lasts roughly till the middle of the transition phase. Once the plateau phase ends and the brightness drops, once the plateau phase ends, the brightness drops almost 3 magnitudes. The transition from the plateau to the radioactive or the nebular phase lasts for around 6 omega naught, and that is roughly 30 to 36 days. So now that we have a good estimate of the distance to the supernovae, the extinction, and the the V band apparent magnitudes, we can plot its absolute V band magnitude as well. So in this figure, using the distance modulus formula, of course, and in this figure, I've compared it with the black dots are of 2013he, and I've compared it with that of various supernovae, ranging from very faint supernovae to very bright or superluminous supernovae. So firstly here we can easily make out how short the plateau phase of 2013he is compared to normal type 2 PSN. And it can also be deduced that 2013he is a fairly luminous type 2p supernova, but not as luminous as some of the well-known superluminous supernovae. So yeah, and compared to other short plateau supernovae like 2006 AI and 2006Y. So the green plot that you can see and the orange one. So compared to those, which are also short plateau, as you can see, it is much brighter. 2013he is much brighter than that. So coming to the spectral analysis of 2013he, this figure shows the evolution of the spectra of 2013he from +2 to +63 days since discovery. The spectra was obtained through various telescopes from around the world, and their flux is scaled to match the photometric flux at that epoch. The general trend observed throughout the evolution of the spectra is that earlier the spectra have a blue continuum, as expected for a young supernova. With time, it gradually becomes redder, and it shows a prominent P Cygni feature, especially in the Edge-Balmer lines, which are the result of expanding ejecta. During the mid-plateau phase, the metal lines also become visible as the temperature falls. Now, I just spoke about this. So comparing the early plateau spectrum of 2013he with those of short plateau spectrum, such as 2000 short plateau supernovae, such as 2007 OD, 2006 AI, and normal type 2p supernovae, such as 1999 EM and 2005 CS. So we can only observe hints of the Edge-Balmer lines that do not very well formed for the short plateau supernovae. And whereas during the mid-plateau phase, the Edge-Balmer P Cygni profiles are very well formed. The HE1 lines now have been dominated by the Na1D lines, so they cannot be distinguished anymore. So yeah, so coming to the analysis of the H alpha P Cygni profile of 2013he provided some very interesting results. So as we saw in the previous slides, it dominates most of the spectra, especially in the late times when it becomes more narrower and deeper. But what is interesting about it is that it shows a low A/E ratio, which is basically the ratio of the equivalent width of the P Cygni profile, absorption and emission components. So basically for 2013he, we're getting a very weak absorption. So this, according to Gutierrez 2018 paper, it is indicative of a fast declining or a short plateau, but a brighter supernova. This could also be indicative of a CSM ejecta interaction in the later phases of its evolution. And the boxy profile of the H alpha emission component also indicates that there might be some CSM ejecta interaction also. And so basically since I've been talking about CSM interaction. So where could this CSM come from? The circumstellar medium come from? So as I mentioned before, the progenitor might have been going through enhanced mass loss prior to the explosion, and the CSM was probably created by this mass loss which the progenitor was experiencing. It is, if it were traveling even at a rate of 10 kilometers per second, say, and over the years it would have spread over thousands of AU around the star. So that could have led to some CSM interactions after the explosion also, ejecta-CSM interactions. And the persistent spike that we observe right above the H-alpha emission feature could be due to the superposed H2 regions from the host. So that was all about the spectral evolution. Coming to the velocity evolution of 2013he. So as the ejecta of the supernovae expands and cools, the rate of expansion slows down, causing the velocity of the expansion to decrease. This is apparent from the plot which shows the evolution of velocities of 2013he, the black dotted line, and compared with that of short plateau supernovae, which I've discussed before also, that is 26ai, 2006y, 2006 AI, and 2016 EGZ, and 2007 OD. So, and a sample of 122 not short plateau, 122 supernovae of Type-II-P and Type-II-L, the gray line is the mean of their velocities, and the shaded regions shows the 1 sigma deviation. Overall, the short plateau supernovae, except for 2007 OD, that seems to be the only exception here. So except for that, the short plateau supernovae seem to lie on the higher end of the distribution, with 2013he lying above all of them, slightly outside the 1 sigma boundary. Such high velocities could be indicative of high explosion energies and more luminous supernovae. Now, to basically derive the explosion parameters of 2013he, we need to, it is imperative to model the bolometric light curve of 2013he. So we use an online Python code called Superbol to integrate the available optical fluxes and to estimate the pseudo as well as the full bolometric light curve. So basically what Superbol does is it computes the pseudo bolometric light curve by directly integrating the fluxes over the observed filters. That is what I had input was BVRI bands only, and gives us L observed, which on the plot we can see as the black dots, and and it also provides us the full bolometric light curve, which is LBB, which we can see as the red diamonds in the plot. What it also does is it basically interpolates for any missing epochs and extrapolates into the UV as well as the IR bands to provide us the full bolometric light curve. We then use a semi-analytical code provided by Nagy and Winco to model this bolometric light curve. This model assumes that the ejecta is homologously expanding and in a spherically symmetric fashion with a uniform density core. The density of the outer layers are exponentially decreasing. And the code basically employs a Markov chain Monte Carlo method for faster optimization. So in this plot, we can see the 12 best fits the bolometric light curve after running approximately 300,000 MCMC Markov chain, Monte Carlo, MCMC loops, and the mean explosion parameters it provides are ejecta mass of 8.33 solar masses, and the radius of the progenitor prior to the explosion being roughly 558 solar radius, and the kinetic energy is roughly 2 FOE, FOE being 10 raised to 51 ergs. And these values lie very well within the range of explosion parameters provided by Hiromatsu et al. 2021 for the three short plateau supernovae that had been studied by that paper. So SN2006Y, 2006 AI, and 2016 EGZ. These three I've also discussed previously in some of the previous plots. And their ejecta masses come out to be in the range of 7.1 to 8.5 solar masses. They are R0, or the radius of the progenitor prior to the explosion comes out to be 450 to 580 solar radius, and kinetic energy also falls roughly around 2 FOE. And the size, the R0 that we've obtained for all these 4 short plateau supernovae are also in the size range of a typical RSG, which is 200 to 1500 solar radius. So using this, we can also get a rough estimate of the mass of the progenitor prior to the explosion. That is 8 solar masses from the ejecta, 1.4 to 2 solar masses for the leftover compact object, and roughly 9 solar masses or so lost due to the stellar winds before the explosion, which gives a total of 18 to 20 solar masses, and which is basically how large a typical red supergiant or an RSG should generally be. Now, this figure shows how the M ejecta and the absolute V-band magnitude of short plateau supernovae compare with those of normal Type-II SNe. And basically because of their stripped envelope, they seem to be much more luminous than the normal Type-II SNe, which we had also seen in the some of the previous plots. Short plateau supernovae, it's apparent from this graph that short plateau supernovae are clearly a different class of Type-II supernovae. So, in conclusion, I would like to say 2013he is a bright but short plateau supernova. Its H alpha P Cygni profile shows signs of CSM interaction, CSM ejecta interaction, and line velocity evolution of 2013he, as we saw, and other short plateau supernovae suggest that they have higher expansion velocities and probably higher explosion energies. From the estimated explosion properties, as we just saw, we have confirmed that the short plateau supernovae could originate from a stripped envelope RSG. In the future, to completely analyze or completely understand short plateau supernovae, we need a larger sample of them. For now, only 3 and plus the 2013he have been properly studied. So we definitely need a larger sample to completely understand them. But as I discussed before, their detection is very rare, but their study is important as it might hold explanations of possible implications to the RSG problem, as well as understanding the controversial existence of the distinction between Type-II and Type-II supernovae. Thank you.
Okay, thank you, Darshana. So now time for questions. Please raise your hands if you have any. No hands raised. I'll wait for a few minutes. Okay, seems like everyone is happy. Maybe I can ask you something, and this might sound like a very naive question. primarily because I also forgot my coursework. I did long time back. So there was a slide in the beginning where you explained about different reactions happening at different times. So I just wanted to know, so just wondering, or just wanted to know why the rate of reaction significantly increases as you move on to higher elements. So for example, from hydrogen to helium, you said it takes 7 million years, right? But the entire silicon is burned up in 1 day, right? Is that what it means, right? So why does this happen? I mean,
so basically the temperature and pressure are also increasing with as we go to successive reactions. So that basically increases the rate of reaction in the.
Okay, so you mean to say the reaction cross section depends on the pressure and temperature, right? Okay.
Yes.
Okay.
May I ask another naive question?
Yeah, sure. Please go ahead.
Yeah, it's a general question. Why do the faster, I mean, heavier masses evolve faster, Harshita?
Sorry, sir. Can you repeat the question?
Why the heavier stars evolve faster?
The heavier stars evolve faster. Yeah. So basically, it's since the mass of the star is very high, it is difficult to basically hold or what can I say, the so I'm sorry, so the mass of the star, since it's high, it is the gravitational collapse that is trying to happen, that will be also a little higher, and the amount of fusion reactions that are happening inside aren't able to balance it out as long as for a smaller mass like sun, a smaller mass stars. So it's crude.
I mean, the stars are the heavier or the smaller mass stars. All stars are balanced, right? So as long as they remain star. The question is why heavier masses evolve faster. What happens if it is a mass is heavier, a star is heavy?
Star is heavy. Also, the luminosity is.
Darshana, will the fusion rate be different in different kinds of different masses of stars?
Yes. Fusion rate. So
So what is the typical temperature of sun, the center of sun? Typical. Okay.
It's 10 raised to 9 or 10 Kelvin. 1.5 into 10 raised
to. Way above.
No, yeah, it is too high.
10 raised to.
Darshana, it's good
Then
that you're
this-
doing research, but
Yeah.
research is not just, you know, you know, sort of taking some data and sort of analyzing that data. You have to also understand what you're doing. So you go through the stellar structure once more.
Yes, yes.
Okay. So why heavy mass stars? I can give you a small answer. This heavy mass stars means the temperature, I mean, the central temperature is very high because the gravity is high. So at the center, it is compressing more. I mean, there's more matter. So at the center, it's compressing more. So temperature is much higher. So the hydrogen will burn up faster because you now have more, the protons are really fast enough. So they will burn higher, but it's not that. It will also go on burning from helium, and as you are burning more and more material, you are also creating a lot of energy, right? So that helps in the reaction rates. So that's why it sort of burns up almost all of the nuclear fuel available. So that's why it evolves faster. Okay. So the reaction rates increases because the temperatures are much higher at the center. And you can estimate what should be that the 10 to the 1, 9, 10, whatever you said. You can estimate for sun, you can easily estimate because you know what is the total mass, right?
Yeah.
You can easily estimate the central temperatures. Try this as a homework problem.
Sure.
You will be able to, you will learn a lot more if you do all these back of the envelope calculations. Okay. All right. Good talk.
Thank you.
Okay. So we have another question in the chat box by Brajesh. He asked, did you perform image subtraction as there is large scattering in the light curves?
Yeah. So for this thesis, I have not yet performed the template subtraction. That is like subtracting the host out of the supernovae, and that's probably why the scatter is occurring. But for the plateau duration itself, the scatter doesn't really, I think, affects the plateau duration. So I was able to go ahead with the rest of the project.
Okay. Okay. Any other suggestion, comments, questions? Okay, seems there are no. So, okay, thank you, Darshana, once again for giving nice talk. And yeah, we'll meet next week with another talk. So till then, take care and bye.